The P-51 Mustang achieved what many thought impossible in 1940. It flew 1,650 miles with a full combat load, effectively changing the course of World War II. This remarkable achievement is just one of many fascinating P-51 Mustang facts, showcasing why this aircraft became legendary. The P-51D Mustang represents one of aviation's most significant engineering achievements. North American Aviation designed and built this exceptional fighter in just 102 days, combining cutting-edge aerodynamics, revolutionary powerplant integration, and innovative manufacturing techniques. The P-51 Mustang's success stemmed from its perfect balance of speed, range, and maneuverability, achieved through groundbreaking engineering solutions that pushed the boundaries of 1940s technology. This video will explore the extraordinary engineering decisions and technical innovations that made the P-51 Mustang so effective, from its laminar flow wings to its game-changing Merlin engine integration. Each component reveals a story of problem-solving and innovation that continues influencing aircraft design today. Revolutionary aerodynamic design. The aerodynamic design of the P-51 Mustang marked a significant leap forward in aircraft engineering. At its core was the implementation of NASA's groundbreaking laminar flow airfoil technology, developed by aerodynamicist Eastman Jacobs in the late 1930s. The P-51 became the first aircraft specifically designed to utilize laminar flow airfoils. This innovative wing design promised to reduce drag by 25 to 50% in theoretical conditions. However, the practical implementation faced challenges. Manufacturing limitations meant that the wings couldn't achieve the surface smoothness required for complete laminar flow. The wing's design offered an unexpected advantage: superior performance at high speeds due to reduced Mach effects. The airfoil shape decreased airflow acceleration over the wing, allowing the P-51 to maintain control at higher speeds than its contemporaries. The P-51 Mustang's fuselage stands as a remarkable example of meticulous aerodynamic design, showcasing a commitment to optimizing every detail for performance. One of the most notable features was its use of flush rivets, which were carefully applied to reduce surface disruption and improve airflow across the aircraft. The engine was encased in a streamlined cowling, designed to further enhance the aircraft's aerodynamic efficiency. External surfaces were kept as clean and smooth as possible, minimizing any protrusions that might cause drag. Among the most innovative aspects was the radiator system, which utilized the Meredith effect, an advanced technique where the heat from the radiator's exhaust generated additional thrust. This system was effective in cooling the engine and contributed to the aircraft's speed and performance. Tests revealed that the removal of surface rivets alone could improve the aircraft's top speed by as much as 10 to 15 knots. The radiator's unique placement beneath the fuselage was also a key feature. It was designed with precision to create no net drag at high speeds. Instead of simply expelling heated air, the exit flow generated thrust that helped offset the drag created by the intake, demonstrating an exceptional level of engineering foresight and efficiency. NASA's wind tunnel testing facilities played a crucial role in refining the P-51's aerodynamics. The aircraft underwent extensive testing at the NACA Langley Memorial Aeronautical Laboratory's full-scale tunnel in September 1943. Hugh Dryden's wind tunnel designs were instrumental in developing the final configuration. The testing program revealed that the P-51's wing design, while not achieving full laminar flow in practice, still delivered exceptional performance. In level flight, the Mustang proved approximately 20 knots faster than the Spitfire using the same engine. This superior speed came from the cumulative effect of multiple aerodynamic refinements rather than any single breakthrough. The combination of advanced wing design, clean fuselage, and efficient cooling system created an aircraft that could maintain high performance at altitudes above 15,000 feet. This capability, coupled with its impressive range, made the P-51 uniquely suited for its role as a long-range escort fighter, engineering the perfect powerplant. The heart of the P-51 Mustang's success story lies in its powerplant evolution, which transformed a capable fighter into an exceptional one. The journey began with the Allison V1710 engine, setting the foundation for what would become a remarkable engineering achievement. The initial P-51 design utilized the Allison V1710 engine, a 1,710 cubic inch displacement power plant that produced 1,150 horsepower at 11,800 feet. The engine featured innovative design elements, including a single overhead camshaft per cylinder bank and 4 valves per cylinder. While the Allison V1710 performed admirably at lower altitudes, its single-stage, single-speed supercharger limited high-altitude performance above 15,000 feet. The breakthrough came when British test pilot Ronald Harker suggested fitting the Mustang with the Rolls-Royce Merlin 61 engine. The results were remarkable. The aircraft's top speed increased to over 400 miles per hour. The Merlin 61's two-stage, two-speed supercharger, designed by Stanley Hooker, delivered 1,390 horsepower at 23,500 feet, compared to Allison's 1,150 horsepower at 11,800 feet. The performance improvements in the P-51 Mustang were significant and multifaceted, elevating its capabilities to a whole new level. One of the most remarkable enhancements was its improved high-altitude performance, allowing the aircraft to operate effectively at altitudes of up to 40,000 feet. This was a critical advancement, as it enabled the Mustang to engage enemy aircraft at greater heights, where many of its competitors would have struggled. Additionally, the aircraft's engine power was significantly boosted, with a 40% increase in power output at sea level. This surge in power provided the Mustang with remarkable speed and agility, enhancing its overall combat effectiveness. The improvements also extended to the engine's reliability, making it more dependable over long missions and in harsh conditions. These advancements ensured that the P-51 Mustang could perform consistently and effectively in a variety of combat scenarios, further solidifying its reputation as one of the most capable and reliable fighters of its time. Perhaps the most ingenious aspect of the P-51's powerplant engineering was its cooling system. The design incorporated the Meredith effect, which transformed what typically would be a performance penalty into an advantage. This system worked by converting engine waste heat into useful thrust, utilizing a divergent-convergent duct design, and offsetting radiator drag at high speeds. The cooling system proved so effective that it could potentially offset up to 90% of the cooling drag. The Packard Motor Car Company manufactured over 55,000 Merlin engines under license, incorporating American production techniques while maintaining the engine's exceptional performance characteristics. The integration of the Merlin engine required careful attention to the cooling system design. Engineers developed a revised radiator with a boundary layer bleed based on extensive wind tunnel testing. This modification, combined with the Meredith effect, helped maintain optimal engine temperatures while minimizing drag penalties. The powerplant's success wasn't just about raw performance numbers. It was about creating a reliable, maintainable engine system. The Packard-built Merlins incorporated standardized American accessories and manufacturing processes, making mass production more efficient while maintaining the engine's exceptional performance characteristics. Materials science breakthroughs. Advanced materials science played a crucial role in the P-51 Mustang's exceptional performance, with innovations in aluminum alloy construction setting new standards for military aircraft design. The P-51's construction utilized sophisticated aluminum alloys, particularly those containing magnesium and copper combinations. These materials demonstrated superior mechanical properties through the formation of metastable and coherent nanoprecipitates of the SL2 QMAG sequence, which produced greater hardening than traditional aluminum compositions. The aircraft's semi-monocoque construction extensively used aluminum alloy, creating a lightweight yet robust airframe. The management of the aircraft's weight was an essential aspect of the design, with engineers carefully controlling the mass distribution across different variants to optimize performance. For example, the P-51 Billion and P-51C models had an empty weight of 6,988 pounds and a basic weight of 7,325 pounds. while the P-51D variant saw an increase to 7,205 pounds empty and 7,673 pounds in basic weight. The weight increase from B, C to D variants totaled 162 pounds in airframe modifications. Despite this weight gain, the P-51D variant achieved significant upgrades that made it even more formidable in combat. Engineers managed to enhance cockpit visibility, providing pilots with better situational awareness during dogfights and long missions. Additionally, the P-51D featured increased armament capacity, allowing for a heavier payload of weapons, thus improving its offensive capabilities. The structural reinforcements also made the airframe stronger, enabling the aircraft to endure more stress and withstand the rigors of extended combat operations. These thoughtful improvements ensured that the P-51D remained a highly capable and competitive fighter, with a manageable weight increase that was more than offset by its enhanced operational performance. The P-51's structural design incorporated several innovative features to maintain integrity under combat conditions. The airframe was divided into 5 main sections, including the forward fuselage, center section, rear fuselage, and 2 wing halves. Each section underwent pre-fitting with wiring and piping before final assembly. This modular approach not only streamlined production, but also facilitated maintenance and repairs. The restoration process of vintage P-51s has revealed the sophistication of these structural solutions. Careful attention to corrosion prevention and material fatigue management was built into the original design, particularly in critical areas such as the fuselage and inboard spars. Surface quality plays a vital role in structural performance. The aircraft featured entirely flush-riveted surfaces, which not only enhanced aerodynamic performance, but also contributed to structural integrity. This attention to detail in manufacturing resulted in noticeably better surface quality compared to contemporary aircraft, demonstrating the advanced manufacturing techniques employed in the P-51's construction. The final combat-ready weight configurations of the P-51 Mustang demonstrated exceptional efficiency, with careful consideration given to both performance and payload. The fully loaded weight of the P-51 Billion and P-51C variants was 9,746 pounds, a configuration that allowed the aircraft to carry the necessary armament, fuel, and equipment without sacrificing speed or agility. The P-51D and P-51,000 variants, which featured further improvements in armament and structural design, had a fully loaded weight of 10,252 pounds. These weight figures represented an optimal balance between structural strength and performance requirements, enabling the P-51 to maintain its exceptional range and maneuverability while carrying a full combat load. Manufacturing innovation. North American Aviation's manufacturing prowess turned the P-51 Mustang from an ambitious design into a production reality at unprecedented speed. The company's innovative approach to aircraft manufacturing set new standards for the aviation industry during World War II. North American Aviation achieved what seemed impossible by completing the first P-51 prototype in just 102 days after contract signing. This remarkable feat demonstrated the company's engineering efficiency and manufacturing capabilities. The prototype first took flight on October 26, 1940, just 149 days into the contract, establishing new benchmarks for military aircraft development. The manufacturing process of the P-51 Mustang integrated several innovative techniques that greatly enhanced efficiency and precision. One of the key advancements was the use of modular construction, which divided the aircraft into 5 main sections. This allowed for easier assembly, as different components could be produced and assembled separately before being joined together. Additionally, the incorporation of pre-fitted wiring and piping before final assembly streamlined the process, minimizing the time needed for these crucial installations once the aircraft was fully assembled. The fuselage design itself was based on mathematical principles using conic sections, a cutting-edge approach that ensured optimal aerodynamic performance while maintaining structural integrity. These innovative design strategies contributed to a more efficient and effective production process, which was further complemented by streamlined production methods that reduced manufacturing time and cost. As a result, the efficiency of the production process saw significant improvements throughout the war. Labor hours required to complete each airframe dropped dramatically, from a high of 12,000 hours to just over 2,000 hours by the war's end. At the peak of production, the factories were capable of completing 20 to 25 aircraft per day, a remarkable achievement in the context of wartime demands. The combined efforts of the manufacturing facilities in Inglewood, California, and Dallas, Texas, played a pivotal role in meeting these production goals. The Inglewood facility was primarily responsible for the production of the P-51 billion, while the Dallas facility took on the secondary production role, focusing on the P-51C variant. To ensure that each aircraft met the highest standards of quality, North American Aviation implemented rigorous quality control systems throughout the entire manufacturing process. These measures included mathematical precision in the design of each component, ensuring that every part was manufactured to exact specifications. Strict adherence to manufacturing tolerances was maintained, reducing the likelihood of errors or imperfections that could affect performance. Additionally, comprehensive testing protocols were put in place to evaluate the airframes and their components under various conditions, ensuring that each aircraft was combat-ready upon delivery. The company also employed continuous improvement processes, refining techniques, and addressing any issues that arose to further enhance the overall quality and efficiency of production. The success of these quality control measures was evident in the field performance, with the P-51 becoming the most numerous variant with nearly 8,000 units built. Total production exceeded 15,000 aircraft of all variants, demonstrating the effectiveness of North America's manufacturing and quality control systems. The manufacturing innovations implemented in the P-51 program significantly influenced post-war aircraft production methods. The combination of rapid prototyping, efficient mass production techniques, and stringent quality control created a template for modern aircraft manufacturing. Combat performance engineering. Combat engineering excellence defined the P-51 Mustang's battlefield superiority, establishing new standards for fighter aircraft performance during World War II. The aircraft's combat capabilities stemmed from three key engineering achievements. The P-51's exceptional range of capabilities came from innovative fuel system engineering. Engineers incorporated an 85-gallon external fuel tank system that extended the aircraft's range to almost 1,400 miles. This breakthrough enabled the Mustang to escort bombers deep into enemy territory and return safely to base. The fuel system engineering included primary wing tanks, a rear fuselage tank, and two 75-gallon drop tanks under the wings. However, this system presented unique challenges. The weight distribution of fuel affected the aircraft's stability, particularly during dives with full wing tanks. Engineers addressed this through careful fuel consumption sequencing, requiring pilots to empty the rear fuselage tank first to maintain optimal balance. The P-51 Mustang's maneuverability profile was a testament to its exceptional engineering, particularly after the integration of the Rolls-Royce Merlin engine, which significantly enhanced its performance. The Mustang's specifications reflected its superior capabilities, with a maximum speed of 437 mph, allowing it to outpace many of its contemporaries. Its combat range of 1,650 miles provided unmatched endurance. The aircraft's service ceiling exceeded 40,000 feet. The aircraft exhibited superior high-altitude performance, maintaining exceptional control at speeds where other fighters struggled. The Merlin engine installation solved previous high-altitude performance limitations, though some restrictions remained due to weight and balance considerations. The P-51's armament configuration evolved to maximize combat effectiveness. The definitive P-51D variant featured 650 caliber Browning machine guns, representing an increase from the earlier 4-gun configuration. This armament proved devastating against both air and ground targets. Combat versatility was enhanced through the integration of rockets for ground attack missions, the capability to carry bombs and napalm, and improved gunsight systems for enhanced accuracy. The weapons system design required careful consideration of weight distribution and aerodynamic impact. Engineers positioned the 6 machine guns to maintain the aircraft's balance while providing maximum firepower. This configuration proved highly effective, enabling P-51 pilots to destroy 4,950 enemy aircraft in air combat during World War II. Despite these impressive capabilities, engineers faced a significant challenge with ground attack missions. The liquid-cooled Merlin engine made the aircraft more vulnerable to ground fire compared to radial engine fighters. This limitation led to tactical adaptations, with P-51s often assigned to high-altitude fighter cover roles while maintaining their ground attack capabilities when needed. Pilot interface design. The P-51 Mustang's cockpit design exemplified the marriage of engineering precision with combat practicality, setting new standards for fighter aircraft interface design during World War. The P-51 Mustang's cockpit layout represented a significant leap forward in pilot workspace design, offering a thoughtfully crafted environment that balanced snugness with comfort. This allowed pilots to maintain control during long missions without succumbing to excessive fatigue. The cockpit featured strategically placed controls, ensuring that they were within easy reach, which was a marked improvement over the cockpit layouts of aircraft from the 1930s. The instrument panel was designed with organization and efficiency in mind, grouping primary flight instruments for quick reference, while engine management controls were positioned for intuitive access. Essential combat systems were also placed within immediate reach, making it easier for pilots to operate the aircraft during high-pressure situations. A particularly notable advancement was the P-51D's signature bubble canopy, which addressed a crucial combat need: the ability for pilots to spot enemy aircraft in all directions. This new canopy design provided several advantages, most importantly offering 360-degree visibility, which greatly enhanced situational awareness during engagements. Additionally, the reduced distortion allowed pilots to better acquire targets, and the improved headroom contributed to better comfort, especially during intense aerial maneuvers. The development of the canopy involved multiple iterations, with British engineers initially pioneering the Malcolm Hood design for early P-51 Billion and P-51C models. North American Aviation then conducted extensive wind tunnel testing with wooden models, refining the final bubble canopy configuration to perfection. The P-51's control systems were also refined based on feedback from combat experience. One of the key adjustments was the addition of a dorsal fin extension, which resolved directional stability issues that had arisen due to the new canopy design. The aileron system was further improved, with leading-edge shields added to enhance control pressure, which contributed to better handling during high-speed maneuvers. The structural components of the ailerons were also strengthened, ensuring that the aircraft could withstand the stresses of combat while maintaining exceptional maneuverability. The integration of the K-14 gun sight in October 1944 significantly improved combat effectiveness, particularly in high-deflection shooting scenarios. This advancement, combined with the hydraulically operated landing gear system, demonstrated the comprehensive approach to pilot interface optimization. The cockpit design proved remarkably effective in combat conditions. Pilots reported comfortable visibility over the nose during landing approaches, while the cockpit's ergonomic layout allowed for extended mission durations without significant fatigue. The seating position enabled pilots to apply the necessary force for high-G maneuvers, with stick forces requiring approximately 25 to 30 pounds per G. These engineering refinements contributed significantly to the P-51's combat success. The combination of improved visibility, refined control systems, and ergonomic design allowed pilots to focus on their mission rather than wrestling with aircraft controls. The P-51D's cockpit became a benchmark for fighter aircraft design, influencing subsequent generations of military aircraft. Testing and validation. Rigorous testing and validation shaped the P-51 Mustang into one of history's most effective fighter aircraft. The extensive evaluation program revealed capabilities that surpassed initial design expectations. The initial flight testing began in October 1940, with test pilot Vance Breeze conducting the maiden flight of the prototype Na-73X. Early testing revealed promising results at low altitudes, but highlighted limitations above 15,000 feet with the Allison engine. A pivotal moment came when Rolls-Royce test pilot Ronald Hawker evaluated the Mustang in April 1942. His assessment led to the transformative decision to test the aircraft with the Merlin engine. The results of this evaluation were nothing short of remarkable. At an altitude of 30,000 feet, the Mustang achieved a speed of over 430 mph. The aircraft's service ceiling reached an impressive 40,500 feet. The Mustang exhibited an exceptional rate of climb of 4,380 feet per minute. Combat testing revealed the P-51's exceptional capabilities in real-world conditions. During Big Week in February 1944, the aircraft demonstrated its superiority by contributing to the destruction of 17% of the Luftwaffe's experienced fighter pilots. Key performance validations included a maximum speed of 437 mph at critical altitude, a service ceiling reaching 41,200 feet, and a climb rate of 4,380 min at low blower critical altitude. The testing program drove continuous improvements through multiple variants. Engineers systematically addressed issues discovered during flight testing. The P-51D prototype underwent evaluation in November 1943, incorporating significant improvements based on combat feedback. The design iteration process proved particularly intensive for the cooling system. Wind tunnel testing at NACA facilities helped optimize the radiator design, validating the theoretical benefits of the Meredith effect. The testing program confirmed that the cooling system could effectively manage engine temperatures while minimizing drag penalties. The P-51 billion testing demonstrated exceptional high-altitude performance, reaching speeds nearly 100 mph faster than the Allison-powered variant at 30,000 feet. This dramatic improvement validated the engineering decisions made during the Merlin engine integration phase. The testing program's thoroughness extended to fuel consumption analysis, with a detailed evaluation of various power settings and configurations. These tests provided crucial data for optimizing combat range and endurance, essential for the aircraft's primary mission as a long-range escort fighter. By early 1944, comprehensive testing had validated the P-51's superior performance envelope. The aircraft demonstrated its ability to escort bombers to targets deep inside Germany and return, a capability that proved decisive in the air war. The testing program's success is reflected in the aircraft's combat record, with P-51 pilots claiming 4,950 enemy aircraft destroyed during World War II. The validation process continued throughout the war, with each variant undergoing thorough evaluation before deployment. This systematic approach to testing and improvement helped establish the P-51 Mustang as the premier fighter aircraft of World War II, setting new standards for performance validation in military aviation. Engineering legacy. The P-51 Mustang's engineering achievements created ripples throughout aviation history that continue to influence aircraft design today. The aircraft's success in World War II, with pilots claiming 4,950 enemy aircraft destroyed, established new benchmarks, fighter performance, and design integration. The P-51's design philosophy directly influenced post-war aircraft development, particularly in fighter design. The success of the Merlin engine integration demonstrated the importance of power-to-weight ratio optimization, with the modified Mustang reaching speeds exceeding 430 miles per hour at 30,000 feet. This performance leap influenced the development of several notable aircraft, including the F-86 Sabre, which adopted the Mustang's aerodynamic principles, the F-4 Phantom, which integrated similar power systems, and modern fighters, which incorporated the Mustang's concepts of cockpit visibility. The aircraft's exceptional range capabilities, enabling escort missions deep into Germany, with loss rates dropping from 16% to below 1%, proved the value of extended range fighters in strategic operations. The P-51's manufacturing legacy continues to influence modern aircraft production. North American Aviation's achievement in designing and building the prototype in just 102 days established new standards for rapid development. Key manufacturing innovations that were established during the P-51's production process remain relevant today, such as modular construction techniques, the application of mathematical precision in design using conic sections, the integration of pre-fitted components, and advanced quality control systems that ensured the aircraft's reliability and performance. The Mustang's development process demonstrated the value of international collaboration. The partnership between North American Aviation and Rolls-Royce, resulting in the integration of the Merlin engine, created a template for modern multinational aerospace projects. The P-51's technical achievements fundamentally changed aircraft design philosophy. The integration of the Rolls-Royce Merlin engine, manufactured under license by Packard Motor Company, demonstrated how strategic component selection could dramatically improve performance. This achievement validated several key engineering principles, including the importance of aerodynamic optimization, as seen in the Mustang's laminar flow wing and low-drag fuselage design. Additionally, the marriage of American airframe design with British engine technology proved the effectiveness of systems integration in creating a performance envelope that surpassed what either country could have achieved independently. The P-51's ability to escort bombers on long-range missions to Berlin and back not only validated the concept of long-range fighter escorts, but also influenced military doctrine and the design requirements of future aircraft, leaving a lasting impact on the development of fighter aircraft for generations to come. The technical impact extended beyond military applications. The Mustang's advanced cooling system, utilizing the Meredith effect, influenced future aircraft thermal management designs. The bubble canopy design, which vastly improved pilot visibility, became standard in fighter aircraft design. The P-51's influence on aviation engineering is particularly evident in its performance statistics. The aircraft achieved a maximum speed of 437 mph while maintaining exceptional range capabilities. This combination of speed and range remained unmatched in piston engine fighters. The engineering legacy of the P-51 Mustang extends into modern aircraft design practices. Its development process demonstrated the importance of rapid prototype development and testing, integration of international expertise, balance of performance characteristics, and manufacturing efficiency. The aircraft's success in addressing the critical need for long-range escort fighters proved that focused engineering solutions could solve complex operational challenges. This approach to problem-solving continues to influence modern aerospace engineering practices. The P-51's impact on manufacturing was equally significant. The aircraft's production demonstrated the effectiveness of modular construction techniques, with the airframe divided into 5 main sections for efficient assembly. This approach to manufacturing optimization influenced post-war aircraft production methods and continues to inform modern aerospace manufacturing practices. The P-51 Mustang is a symbol of wartime engineering excellence, blending innovative aerodynamics, powerful engines, and efficient manufacturing. North American Aviation's achievements revolutionized aerial warfare, creating the perfect balance of speed, range, and combat effectiveness. The Mustang's legacy continues to influence modern aerospace design, demonstrating the power of international collaboration. Its development proved that focused engineering can solve complex challenges and push technological boundaries. The P-51 Mustang remains a shining example of human ingenuity. What do you think made the P-51 such a game-changer in aviation history? Share your thoughts in the comments. If you like this video, please comment one to let us know. Thank you for watching. See you in the next videos.